In this video, I'd like to go through one of the problems on my PowerPoint notes. And in this problem, we're going to run through a hypothesis test for the proportion. Now, there's a few different ways it could play out. Hopefully, you would have seen this by now. A one-tail test or a two-tail test, and that one-tail test could be right tail or left tail. So we'll see if we can figure out what's going on here in this problem. So based on the information from the National Cybersecurity Alliance, 93% of computer owners believe they have the antivirus program installed on their computer in a random sample of 400 scanned computers. It is found that 380 of them actually have the antivirus software. Use the sample data from the scanned computers to test the claim with 5% or 0.05 significance that 93% of computers have antivirus software. So what I have over here on the left, I sort of have this set up in terms of how you would go through the problem step by step. And as always, with any hypothesis test, we want to start with expressing the claim symbolically. So to test the claim with 0.05 significance that 93% of computers have antivirus software. So what I have here highlighted, that is the claim. Okay, so this is saying that the proportion, and remember, percentage, proportion, these two words are interchangeable, more or less. And normally a proportion is given as a decimal, a percentage is a percentage, but they're more or less interchangeable. So the claim is that exactly 93% of computers have antivirus software. So the proportion equals 0.93. So that's the claim that we're testing. There's no mention in the problem about more than, less than, greater than, at least, at most. So there's nothing in the wording that tells us it's an inequality. So our claim is equal. The null hypothesis, remember that's always a statement of equality, so the null hypothesis would also be P equals, so actually let's use the notation here. The null hypothesis, H0, would be the statement P equals 0.93, and the alternate hypothesis, which we use H1, some books use a little a down there instead of the 1, either way, would be that the population proportion is not equal to 0.93. Now, let's see if we could use some of this information that's given in the problem. And my color coding down here is yellow are spaces where I'm gonna, or cells where I'm gonna type something in, and blue is something where I want Excel to do the calculation for me. Okay, so let's go back to the problem. Based on information from the National Cybersecurity Alliance, 93% of computer owners believe they have an antivirus software. So that's P. That's the population proportion. So let's put 0.93 in there, or the assumed population proportion. And in the sample of 400 scanned computers, so that 400, that is our sample size. So N is 400. It is found that 380 of them, so that's the number of successes, or X, actually have the antivirus software. And we're testing the claim with a 0.05 significance. Okay, so that's the information given in the problem. P hat is the sample proportion. Now that's P hat, I'm just writing there, but that's the P with the little upside down V looking thing above it. So that's what I mean by P hat. That's the sample proportion, and that should be equal to X over N. So we have X and N up here. So equal to X divided, you don't want that, X divided by N Okay, and down here, the Q, so you see our sample proportion is a little higher than our assumed population proportion. And so Q is the complement of P, so if P is this 0.93, then the Q should be equal to 1 minus the P. So that should give us 0.07, and yes, it does. Okay, so now we're using the normal distribution as our model here. And remember, the alternate hypothesis is what tells you whether it is a right tail, left tail, or two-tailed test. And if you look down here at the bottom left, you see there's two sheets in this file. The problem is on the first sheet, and under charts, we have sort of some visual aids and tables here. Up here, our choice is whether to use right tail, left tail, or two tail. It's the sign that's used in the alternate hypothesis. So not equal to is a two-tailed test. Okay, so we know that our critical region is split halfway, half in each of the two tails. Okay, so there's a critical value here. There's a critical value here. And the area of that critical region combined between the two tails is alpha. That's the significance. And so the area of each tail would be half of alpha. Zero 0.025. Okay, so we need to figure out the critical values. And so I have, I'm going in order. The way I have these things listed here on the left, you need the significance to find the critical value. Okay, and they're going to be the same number. So this is 0 in the middle. The graph is symmetric. So this positive critical value and this negative critical value, they're going to be the same number. Just one positive and one negative. And we could figure that out. In this case, equal norm.s.inv. And in this case, we could use 0.025. That will give us this negative critical value here, negative 1.96. But we want to use the positive one in our test statistics, so let's go back into that formula and just throw a negative sign in there. So we're basically taking the negative of the negative critical value. There's a few different ways you could go about this. Okay, so now we know our critical values, 1.96 and negative 1.96. Now you want to take your sample data and see where it lies, whether it's in the critical region or not. And your sample data is converted into this test statistic. And so your test statistic, in this case, is a z-score. And it's the difference between the sample statistic of the proportion and the population parameter of the proportion divided by the standard error between the two, which is the square root of p times q divided by n. Okay, so we want to put that one in there. And what I'll do is I'll put some parentheses around the numerator just so we preserve the correct order of operations. Parentheses can't hurt. Okay, so that's equal to p hat minus p. So I'm just typing in the locations of those values. Oops, I said I would put in parentheses. Okay, equal p hat minus p in parentheses. Okay, divided by the square root, sqrt, of p times q divided by n. So n is up here in B14. And we'll close those parentheses. All right, so this is our test statistic. So it's basically our sample data converted into one singular number, some single representative number. Now, you'll see that this test statistic, which is right here, well, it looks like it does not fall in the critical region. So our test statistic is this z-score. We'll say TS for test statistic. And that's 1.568. So it's closer to 0 than the critical value. So that tells us that we fail to reject the null hypothesis. We fail to reject the null hypothesis. And if we are using so that's the traditional method, is comparing the test statistic to the critical value. That's the traditional method to tell us what to do with the null hypothesis. And then there's the p-value method, which is just another way of doing the exact same thing. The p-value, well, we need to figure out this area outside of that test statistic and then double it. We don't always double it, but we double it with a two-tail test. So this area should equal, well, let's do it in this cell over here. So we'll use the normal standard distribution function in Excel. Equal, and we want area to the right, so we need the complement of the area to the left. Excel only does area to the left, so equal 1 minus norm dot s dot dist, and our z-score, that's our test statistic. So I can just click on the value over here, and cumulative, yes, we always say yes, so true or the number 1. Okay, so that is the area outside the test statistic, and for the p-value we have to double that. So over here under p-value we'll say equal 2 times this number. Okay, so the p-value in this, for this particular problem, is greater than the significance. So that tells us to reject the null hypothesis. So this question of whether or not we reject the null hypothesis, it can be found using the test statistic and the critical value, or it can be found using the p-value and the significance. Either way, you're going to get the same result to reject the null hypothesis. Now, for the final conclusion, so remember, one, we cannot prove a claim is true if the original claim contains equality. Plug over here to the other sheet where I have the chart, and this down here on the bottom right, we can make this a little bit bigger. Does the original claim contain the condition of equality? Yes. So we're not going down here. The original claim was p equals 0.93. Do you reject the null hypothesis? No. So we're down here. So that puts us at this box here. There is not sufficient evidence to warrant rejection of the claim. So basically the test is inconclusive. So the original claim is the population proportion is 93% or 0.93. The sample data says no, it's actually 0.95. But the result of this hypothesis test is that the sample data, even though it says something different than 0.93, it's not compelling enough evidence. It's not strong enough data. So in this case, the test is inconclusive, which means basically collect more data. Okay, so let me just go back over here. Not sufficient evidence to reject the claim. Not sufficient evidence to reject the claim that the population proportion is equal to 0.93. Okay, so this was an example of a two-tailed hypothesis test for the proportion. As I said, it could also end up being a right-tail test or a left-tail test, depending on the alternate hypothesis. That is how you choose which type of test it is. All right, that does it for this problem. I hope this was helpful.